Alright, in this video we're going to use the first derivative test on a couple of examples just to find relative maximum and relative minimums. So for this first example, let's find the relative extrema of f of x equals 2x to the third minus x to the fourth. And we'll say sketch the function. So first off, to find relative extrema, the first thing you want to do is find critical values. And to find critical values, remember we want to find where either f prime of x equals 0 or f prime of x doesn't exist. So first thing we got to do is find f prime of x. So f prime of x is equal to, taking the derivative here, we get derivative of 2x cubed is going to be 3 times 2 is 6x to the second power, minus the derivative of x to the fourth is minus 4x, right, bringing the 4 down in front, so minus 4x to the third power. And then to find critical values, alright, so to find CV for critical values, we set f prime of x equal to 0, or find where it's undefined. And, you know, in this case, nothing will be undefined because this is a polynomial, so we know that the function exists at all x values. So we're just going to find where it's equal to 0. So I'm going to set 6x squared minus 4x cubed equal to 0, and we're going to solve that. You should always try to solve by factoring first. Trying to factor this out, looking for a greatest common factor, I know I can take out 2, and x squared and x to the third have a common factor of x squared. So I'm going to take out a 2x squared, and then what's left inside? Well, 6x squared factoring out the 2x squared leaves me with 3, minus the 4x cubed factoring out the 2x squared gives you minus 2x. The whole thing equals 0. And then once I've done this, remember you want to solve for each variable equal to 0. The 2 never will equal 0. The x squared equals to 0. And the 3 minus 2x we set equal to 0. Solving this, x squared equals 0. You take the square root of each side. You just get x equals 0. You could also just know that x to any power equaling 0, that number has to be 0. So you get x equals 0 there. Here, to solve this, you know, I'm going to add 2x to each side. So I end up with 3 equals 2x. And remember, you're trying to solve for x, so we're going to divide by 2. And divide by 2, I end up with x equals 3 halves. These are the critical values, right? That's what we are trying to find. Critical values occur when f prime of x equals 0. These are the x values that make that 0. Or where f prime of x is undefined. In this case, you know, there's no problem points, so it's defined everywhere. And then we want to use the first derivative test. Remember how the first derivative test works. We're going to make a number line. Remember, this number line is for f prime of x. And we're going to put our values on the number line. So we're going to put our values in order. We'll put 0 here first, then we'll put 3 halves here after it. And you want to test values, remember, to the left and right of each of your critical values to determine if f prime of x is positive or negative there. So if I was to test here and say we want f prime of something to the left of 0, I'll pick negative 1. So f prime of negative 1, remember you're substituting into f prime of x. Now you could substitute here or here, but you're substituting f prime, not the original. So this would equal 6 times negative 1 squared minus 4 times negative 1 to the third power. And that's going to give me, calculating this, negative 1 squared is just going to be a positive 1 times 6 will be 6 minus negative 1 cubed is a negative. Negative times that makes that a positive 4. So 6 plus 4, this equals 10. And remember, what do I care about? The sign. The sign here is positive. So I know that for the values to the left of 0, like negative 1, f prime of x is positive there. Remember, I don't care about the number. I only care about the sign of the number. So if it's positive there, what does that tell you about the original function? F of x is doing what? Well, if the first derivative is positive, it tells you the slopes of the tangent lines are positive, so it's telling you f of x is increasing, right? It's rising from left to right there. You have to pick something between 0 and 3/2. You can pick anything you want. I'll try f prime of 1. That's easier to work with. 3/2, remember, is like 1.5, so f prime of 1 will give us 6 times 1 squared minus 4 times 1 cubed. 1 squared is just going to be 1, so it's going to be 6 minus 4 times, this is just going to be 1, so 6 minus 4 gives me 2. 2, what's important about it? The sign is positive. So between 0 and 3/2, I know that my first derivative is positive. The first derivative is positive. What does it tell you about the original functions? Well, remember, this is the slopes. The slopes are positive, tells you that f of x, the original function, is increasing there. And then, right, because these slopes are moving upward. And then for 3/2, or to the right of 3/2, I should say, I can pick anything I want. So I'm going to pick 2. You could pick 2,000 if you wanted to. It doesn't matter as long as the number is to the right of 3/2. F prime of 2 is equal to 6 times 2 squared minus 4 times 2 cubed. And we'll evaluate that. 2 squared will be 4. 4 times 6 is 24. Minus here, it's going to be 24 minus 2 to the third is 8. So minus 4 times 8 is 32. So 24 minus 32. When you do that, that gives you negative 8. The thing I care about is that it's negative. If this is negative, what does it tell you about the original function? Well, the first derivative being negative over here tells you that the slopes are going downward. If it's going downward, then f of x is decreasing. So let's talk about what's happening. So you know that f prime being positive tells you that the slopes are increasing, means f of x is going upward. And then here the slopes are positive, f prime of x increasing is going upward. So it's going upward, and then after 0, it flattens at 0, because we know that f prime is 0 at 0. And then it goes upward again. So at x equals 0, we don't have a max or a min, because it's going up, and then it's still going up. So it didn't go back down, which would have caused it to become a maximum. So at this point, at x equals 0, is neither a relative max or a relative min. And that's okay, that can happen. And then at 3/2, right, so we are increasing here. Remember, f prime of x being negative tells you your slopes are going downward, which means f of x is decreasing. So now I'm going up and then I'm coming down. So if I'm going upward and then coming down, what do I have here? Well, if I go up and then come down, I have a relative maximum. So at x equals 3 over 2, we have a relative maximum. Now remember, when I say this, right, this is just where the maximum will occur. It's not what the maximum is. So, we use the first derivative test to determine where the relative extrema occur. Now we got to find the corresponding y values. So let's sub in. Now we don't have to sub in 3/2 to find the corresponding y value, because that's the only one where we have the relative extrema. So we want to sub into, remember what you're subbing into. You sub into f of x, right, the original function, to find the y values that go along with this. So the original function f of x, just reminding you way up here, was 2x to the third minus x to the fourth. So f of x was equal to 2x to the third minus x to the fourth. We're looking for f of 3/2. So f of 3/2 would equal 2 times 3/2 to the third power minus 3/2 to the fourth power. And we can evaluate this. You end up with here 2 times, when you have a fraction in here raised to a power, you can raise the numerator to the power and the denominator to the power. So 2 times this will be 27 over 2 to the third is 8. So 2 times 27/8 minus here, same thing, 3 to the fourth will give me 81 over 2 to the fourth is 16. And I end up with, you can simplify this by getting a common denominator. 2 times 27 would be 54 over 8 here. And then multiplying by another 2 to get this, we end up with 108 over 16 to get a common denominator, minus 81 over 16. And that's equal to 27 over 16. And if it doesn't reduce, in which this case it doesn't, that's okay. So this value, though, is the relative max, right? The relative maximum is 27/16. It occurs at 3/2. Or you could say, your relative max is at the point 3/2, 27/16, understanding that the y value is actually what we call the maximum. There is no relative min in this case. We don't have a relative min, and that's okay. We did ask you to sketch the function, so to sketch this function, you want to kind of use the points that you know to help you. Since we already know we have x equals 0, you might as well find the y value that goes along with it. So add x equals 0. F of 0 would equal what? Well, it's going to be 2 times 0 cubed minus 0. It's all going to be 0. So we know that at x equals 0, f of 0 equals 0. So we have the point 0, 0. But all we know is that that is on the graph. It's not a relative max or a relative min. It's neither, and that's okay. So to sketch this graph, we have our relative extrema, and that's what we wanted. We also should use our x and y intercepts if we can. Sometimes it's easier than others to find them. If I said to find the x-intercepts for a graph, remember the way you do that is you set y equal to 0. I'm going to set 2x to the third minus x to the fourth equal to 0. That's the original function. And to solve this, what do? Well, you factor. So I'm going to factor out x to the third. I end up with 2 minus x equals 0. Solving this, right, x to the third equals 0. 2 minus x equals 0. The first part, x to the third equals 0, just gives me x equals 0, right? Taking the cube root of each side. So I know I have the point 0, comma 0. That's one x-intercept. We already kind of knew that because we had it before. The other one, 2 minus x here, remember I'm going to add x to each side. So I get x equals 2. So I know I have the point 2, comma 0 on my graph, right? X, comma y. These are the x-intercepts. Make sure you know that's what we're finding, right? So these are the x-intercepts. To find the y-intercepts, right? Find the y-intercepts. In this case, it's not too bad because to find the y-intercept, you set x equal to 0. There's only going to be one y-intercept at most. So you set x equal to 0. While doing that, right, we'd have y equals 2 times 0 cubed minus 0 to the fourth. It just equals 0. So we'd have the point 0, 0, which we already knew, but this is the y-intercept. So if I went to sketch this, right, so I'm going to sketch everything that we just talked about. Here's our sketch. We're going to have an x and y axis. Here's x, here's y. I can plot the intercepts that I just talked about. So I have the x-intercept at here's 0, 0, and then I'm going to have, let's go 1, 2, 3, 4, just to kind of make this, a little more clear, but you don't need to have it that accurate. So you got 0, 0 here. We've got 2, 0 here. Y-intercept is 0, 0. We're already there. We have this point here, 0, 0, that we knew from earlier. We already got it on the graph. And then the relative max is at 3/2, 27/16. Think about where that would be. 3/2 is 1.5, so it'd be in the middle here. 27 over 16. Think about where that would be. 32 over 16 is 2, and 16 over 16 is 1. So it's between 1 and 2, closer to 2. So if I was looking at this, I'd put it right about there. And this is our relative, what? It was our relative max. So we have a relative max, and this is at the point 3/2, 27/16. Leave it as a fraction, that's okay. And let's talk about what happens. So we're going to use our first derivative test along with, our values. We know it's relative max to determine what happens here. So to the left of 0, f of x is increasing. And then at 0, right, we know it flattens out. That's what f prime of x equals 0 means, right? It flattens. The slope of the tangent line is 0 there, and then it increases again. So what's really going on when I go to graph this is I'm increasing until I get to 0. It flattens for a second right at 0, and then it goes back up. Right? So it's increasing and it's still increasing. It's increasing until you get to 3/2. Once you get to 3/2, you get there, it flattens out and then comes back down. So we're going to go up to here. Right? Flattens out. That's why we find it, because that's going to make it a relative max. And then it decreases. Now this says it decreases where? It decreases everywhere to the right of 3/2. So this is telling me it's going downward forever through that side. And this would be your sketch of f of x equals 2x cubed minus x to the 4th. So, when we go to sketch these, we want to make sure we put these key points on the graph. I drew an axis on this one in the previous example. In the last video, I didn't. Mainly because, sometimes these values get a little out of hand in terms of how large they are. But if you can graph them on a grid like I just did, you probably should. It gives you an idea of what the shape really looks like, though. And, using what we did when we set up our first derivative test tells you how the function behaves on each interval. Let's take a look at just one more. If I said to sketch this one here, so sometimes they might just say sketch the graph. So sketch the graph of g of x equals the cubed root of x squared plus 2. So first off, I'm going to rewrite this. And I want to rewrite it as g of x equals, remember I want to rewrite the radicals in exponent, so this would be x to the 2 over 3 power, right? That's the index of the root, plus 2. Okay, so make sure you rewrite first. And then what do I need? Well, to find the critical values, I need the first derivative, so I need g prime of x. Well, taking the first derivative here, I end up with, remember how this works, power rule brings it down in front, so I have 2/3 x to the negative 1/3. Derivative of 2 goes to 0. And then just simplifying this, I'm going to write this as g prime of x equals negative exponent, tells you to move it to the denominator, so you got 2 over 3x to the 1/3 power, which would be the cubed root. Yeah, I'll write it a little more clearly here. 2 over 3 times the cubed root of x. So that's just rewriting the derivative. Now let's talk about how do you find critical values. Well, critical values occur when you want to set either the first derivative equal to 0 or where it's undefined. So let's take a look at when g prime of x equals 0. Well, for this is a fraction, right? This is g prime of x. We got 2 over 3 cubed root of x. The only way a fraction can ever equal 0 is if the numerator is 0. And in this case, the numerator will always be 2. That can't change based on what we have here. So for g prime of x equals 0, can this ever equal 0? The answer is no. So this isn't possible. All right? So this is not possible. So there are no critical values that we get from where the first derivative equals 0. And that's okay. Or, remember the other way, or it's where the first derivative g prime of x does not exist. So are there places where this does not exist? Well, let's take a look at our domain of g prime of x. G prime of x, you want to set the denominator equal to 0. Well, the denominator equal to 0, when does this equal 0? Well, you've got, 3 cubed root of x equal to 0, and we want to find those values because that's where this wouldn't exist. That would make this undefined. Well, you could divide both sides by 3 here. You have the cubed root of x equals 0. And then to get rid of the cubed root, remember you're going to raise each side to the third power. You end up with x equals 0 to the third power, which is 0. So x equals 0, right? This is critical value. All right. You might be able to tell that right away. If you can see it right away, that's great. You can just say x equals 0 makes this undefined. Sometimes if there's a polynomial in here, you might do a little bit more work to get there. So x equals 0 is our only critical value. So if I'm using my first derivative test, remember how the first derivative test works. I'm going to set up a number line. I'm going to put my critical value on here of 0. And this is a number line for f prime of x, remember. And when I do this, right, this is a number line for f prime of x, I want to test values to the left and right of this in our derivative. Actually, I should call this g prime, right? This function is g. So g prime of x. But it's a number line for the first derivative. Then I'm going to sub in values to the left and right of this to test if g prime is positive or negative on each side. So if I use g prime of something to the left of 0, I'll say -1. You end up with 2 over 3 times the cubed root of x is -1. This ends up being 2 over cubed root of -1 is a -1 times 3 is -3. The important thing, remember, is we care about the sign of this. A positive or a negative, this is going to be negative. So I know to the left of 0, g prime of x is going to be negative. Well, what's that tell you about the original function? Well, it tells you the slopes are going downward, so it tells you that g of x is decreasing there. And if I try something to the right of 0, so let's say g prime of +1, remember, you can pick whatever you want. We got 2 times 3 cubed root of 1. Well, cubed root of 1 is 1. 1 times 3 is 3, so this is 2/3. The important thing, though, is that this comes out to be positive, so I know I'm positive for g prime on the right side of 0. So if g prime is positive, it tells you the slopes are positive. If the slopes are positive, it tells you that the original function g of x is increasing. And then you have to ask yourself, well, what kind of extrema is 0? Is it a relative max, a relative min, or neither? Well, it's going downward and then coming back upward. So if it's going down and then coming back up, right? It's decreasing then increasing, right? Then you're going to end up with, we have a relative, right? Going down and coming back up. That's going to be a low point, so it's going to be a relative min at x equals 0. So you have a relative minimum at x equals 0. Remember, you want the corresponding y value. To find the y value, remember what you do, you sub into the original. So, all right, we want g of 0 now. Well, g of 0, we're subbing back into g of x, which was the cubed root of x squared plus 2. So it's the cubed root of 0 squared plus 2, which just ends up being 0 plus 2, which equals 2. So remember, 2 is actually, right, the relative min, right? That's the relative min value. And, or you could say, another way of saying it is relative minimum at the point x comma y is 0 comma 2. So let's talk about the sketch of this would look like. If I was talking about finding the graph here, here's x, here's y. We know we have a relative minimum at 0, 2. So 0, 2 would be right here. All right, we have a relative min. And the other thing I know about this is the information they gave me about the derivative. If I was looking for x and y-intercepts, though, to find x-intercepts, it's not going to happen because if this is decreasing, if you're looking at this, decreasing until you hit the minimum and then increasing, you're going to be going downward to here and then upward after it. You're never going to hit the x-axis. So you could try to find x-intercepts by setting y equal to 0, but there wouldn't be any. The y-intercept, you're already on the y-axis, so you already have that part down. But let's talk about what's happening here. And then, as we get into the next section, we'll be a little more accurate with it. But we know that, at 0, right, x equals 0, this is where the first derivative was undefined. So we know it's not a smooth transition from decreasing to increasing here. because it wasn't when g prime of x equals 0. So it's not a slope of 0 here. It's actually where the first derivative doesn't exist. So it means I have a sharp point. So what really happens in this graph, and we'll see it more in the next section, is this kind of comes down here until you get to the point, hits the point, and then that's decreasing, right? Because decrease till you get to 0. So it's going to come downward here until you get to here. And it's a sharp point, and then it increases everywhere afterwards. So then we're going to go up like this. And we have this, you know, this sharp point kind of cusp type thing where it's coming down this way, going up this way. But, you know, the slopes from each side weren't going to the same value. They weren't approaching 0, so it wasn't going to be flat. It's going to be a sharp point. But we have a relative minimum here at 0, 2. This is a rough sketch. Sometimes people will add extra points in here. If we're sketching it, I only care about the key values you have on here. If you did try to find the x-intercepts, there wouldn't be any, mainly because of the shape of this graph. But if you were to set, you know, y equal to 0 and try to solve for it, you'd get something that had imaginary solutions, and that's how you would know. Hopefully this helped in doing a couple more examples of first derivative test. We'll talk about second derivative test in the next video, which actually is another way of doing the same thing.